In this video, we're going to be talking about extrema. And what that is when you have a function on a graph, say a function that looks like this, you're going to have certain points on your graph that are critical to understanding what is going on. And these points are called critical points. Well, what are some of the most important things that we need to know when we look at a graph? Well, that's going to be where you're changing direction. Say this was an example of hopefully not your business finances because they're taking a plummet, but you can tell though that you have changes of direction. There comes a point where you're going up and then you have a point where you're decreasing and then increasing again. Well, right here you can tell that we have 2 points where they're extremes, relatively speaking. Now, what do I mean by relatively speaking? Well, this is a relative maxima. So we'll call this a relative maxima. And this is a relative minima, or minimum. We'll just say minimum to be maximum. There we go. Okay, and what I mean is that this graph goes on forever. So it's not an absolute maximum, because if it just goes on and on and on, well, it's never really going to cap out if the function just goes on. And it's never really going to bottom out. But if we sort of cut what we're looking at into a little section called a closed interval, which you'll see in notation looks kind of like this. And then you're going to have an area where you have a relative maximum. Now you're also going to have a lot of other areas that would be considered lower, on and on. But these are the max areas within this closed interval. Now, since we've learned how to, up to this point, if you're looking at extrema, you've learned how to take a derivative, set it equal to 0, and then, find your second derivative and set it equal to 0 and solve for x. Well, now we're going to be actually applying these things so we can get information about a whole bunch of really cool things. But we have to lay the groundwork first. So let's do an example. So say you get a problem that says locate the absolute extrema of the function f of x equals x cubed minus 27x on the closed interval 0, 4. You notice those little brackets? They look a lot like those. Now, this is not the graph of this function, but it's just an example. Now, see here how it says, absolute extrema. Well, these are now the absolute, but they're only considered absolute extrema because it's on this closed interval, and we're just cutting our graph off. We're ignoring that we have these things increasing and decreasing, for forever. So what we're going to do is we're going to look at our function right here, and we are going to take the derivative of this function and set it equal to 0. So first thing we have to do here is take our derivative. So that's going to be f prime of x equals 3x squared minus 27. Then we have to find out where our first derivative equals 0. So let's write this down. We're going to take the derivative. All right, let me take the first derivative of your function. Or g of x, whatever it is, right? It's just a function. And then you're going to set that first derivative equal to 0. Okay, so where does this derivative equal 0? Well, we'll have 27. We can move over here. We have 3x squared. We divide by 3. We have x squared equals plus and minus the square root of 27 divided by 3. But remember, when you are doing these, you want to simplify everything down as much as possible, which, speaking of that, oh no. Oh, I could make this a little bit easier. Okay, let me do it this way first. So we'll say plus or minus, and now square root of 27 over square root of 3. This ends up being square root of 9 times 3 over square root of 3, which equals square root of 9 is 3 times square root of 3 over the square root of 3. Well, that's going to cancel, and we get that x squared equals plus and minus 3. And I don't know why I put the squared back in there. Probably because I was looking at that guy. Okay, so x equals plus and minus 3. All right, so we've solved for that. Well, if you go back to up here where I had my first derivative, and a big thing we're going to see with something simple like this, it didn't make that big of a difference. But if I would have done this, if I would have simplified better, or not better, but if I would have simplified more efficiently, I would have taken a 3 out of each of these, and I would have had x squared minus 9. And then I would have set this equal to 0. Well, what's going to make this equal 0? 3 is never going to equal 0, ever. It's always going to be 3. But this could make the whole derivative equal to 0. How? Well, if you don't see it, that's fine. You can say x squared equals 9. So x is going to equal plus and minus the square root of, square root of 9, which equals plus and minus 3. And if you see this right here, that was a lot less work than this, having to do that and then reduce my root and then cancel these roots. So it's a really big deal to simplify. Let's put this up here. Simplify as much as possible before setting f prime of x equal to 0. Okay, so then now that we have found that we have these values, what are these values? Well, these values are your critical values. Okay, so what does that mean? That means that at these values, you're having something happen, and it's going to be happening. Let me see if I can move this. One of these, you may have a relative minimum or a relative maximum. Well, how do you tell which is which? Whoops. Man. If I can move this. Okay, how do you tell which is which? Well, we're going to do a number line. Now, we are on an interval, 0 to 4. So we have this number line. We'll do it in blue. And we have the number 0 on the end. And we have, I'm going to do these really big, 0 and 4. Okay? But then we also have minus 3. Because these are our critical values. We're going to put these critical values, which are the values of x that make your first derivative equal 0. Those are your critical values. We're going to put them, whoops, give me some space. We got 3 right here. Now, we have, the reason I left a bunch of room, which isn't really symmetrical room, but that's okay, is we need to take some test values. Test values are just values that are in between. So we need a test value here, a test value here, a test value here, a test value here, and a test value here. And this is going to give us information about our graph. It's going to let us know where our graph is increasing and where our graph is decreasing. So let's do this. All right, so we have here that, let's see, before -3, let's do like -100. We'll do negative 100, okay? Because it doesn't matter what my number is. I just want, and I'm going to plug these test values. So let's write that down up here, because I think it's helpful, at least it's helpful for me, so maybe it will be for you, to make a list of steps to do. Okay, so now you found f of x equals 0, then you need to solve for x. This is going to give you your critical, no, not points. Points require a y. This is going to give you your critical numbers, and then you need to do a number line with test values. Then you need to plug your test values into the first derivative. So not into the function itself, but into the first derivative. Okay. So we have negative 100. Well, what's between? It doesn't matter, by the way, what number you pick. It just has to be in between. All right, so we can just do 1. Wait, this is negative 3 and 0. So let's do negative 1. So negative 1. And then 0, we'll do 1. I'm a big fan of 1. And then we'll do between 3 and 4, we can do 3.5, which ends up being what? 7 over 2? Is that 3.5? 3 times 2 is 6, 7. Yep, bam. Some moments. It's the little things. Okay. And then we're going to do plus 100 over here. All right, so now we need to plug these into our first derivative, which we can use this really easy part of our first derivative. Oops. Which, if I can find, here we go. All right. Probably should just rewrite that. Okay. So now we're going to plug this in. So say we have f prime of negative 100. All we want to know is the sign, right? We don't care what the actual number is. So if I have 3, and then I do negative 100 squared minus 9, well, this is going to be a positive number, because this is going to give me a positive minus 9, right? And it's a big positive. So this is going to be a positive. When I get a positive, that means that I am increasing. My graph is increasing on this interval. What is this interval? This interval is negative infinity to negative 3. So how do I show that on my graph? Well, here we go. Increasing. Bam. All right. So now we're going to do f of negative 1. And so we're going to do it again. We're going to look. We have negative 1 squared minus 9. Well, now, even though this negative 1 is going to become positive, we're going to have a negative. It's going to be 1 minus 9. So that's going to be a negative. And you'll see, let's see, this is decreasing on the interval negative 3 to 0. So you're not worrying about, you're not cutting off your interval at your test value. It's going to take care of the whole interval in here. Now, what happened here? Well, I changed direction. That's what happens at critical points. At critical points, your graph is changing direction. It's changing what it's doing. It's going from, either decreasing to increasing, or, on and on and on. This is really cool that we're finally seeing that we can do something with what we've learned, right? Okay, so we're decreasing there. Now, what about between 0 and 3, which is here and here? We're going to plug in this 1. So we have f of 1 equals 3 times 1 squared minus 9. Same thing, still decreasing. Why did I put a 0 there? because this is just my, okay. I was actually asking that to myself. Okay, because that's the end of my interval. So when we look at this then, it's important for us to realize that we're only taking values from 0 to 4. So we found these things out, but we have a closed interval from here to here. So these are the only parts that this problem is asking us for. So if you were to give all this information, it's great to know, but you don't have to put it for this particular problem, but still good to know for what we're going to be doing. Okay, so when it's on a closed interval, you could actually make your number line just 0 to 4 and not do these other sections. Okay, so now let's go ahead and do f of 7 over 2. Okay, so now we have 7 over 2 squared minus 9. Well, 7 over 2 squared is 49 over 4 squared, which is what, 12? So this is going to be, now that we know, is that, no it's not. Lies. It's almost 12. Whoops. 40, let's see, what is it? Put it in my calculator. 49 divided by 12. How did I? Oh, it's 49 divided by 4. Okay, 12.25, so it's almost 12. I say one thing and then my hands just do it. Okay, so 12.25 minus 9. Well, this is positive. So that means we are increasing on the interval 3 to 4. All right, so we have increasing. So now, if we look, we're not even going to do the other part, which we could, but we're not going to because we're only doing the closed interval. If you look here, what does this look like to you? Looks like you're going down and then going up. Do you see that? That means you're going to have, if it's on a closed interval, it'll be absolute. If it's not on a closed interval, then it's going to be relative because it's only relative to the area that you're looking at. So absolute, this is a minimum of your graph. Do you see that? How cool is that? Okay. So if I can zoom out now, I zoomed way in. One day I might be able to get this down. Okay. So if we go back to our question then, and it says locate the absolute extrema of the function on the closed interval. Well, even though that we got x equals plus or minus 3, the only value that is going to answer this question for the closed interval is going to be x equals 3. So at x equals 3, we have an absolute minimum. Now that we found that we have an absolute minimum there, what we want to do, because it says to locate all of the absolute extrema, so what we're going to do is we're going to plug in all of our values. So we are given endpoints. We're going to plug these into our original function. So I can move this. Move this down here so we can see. The next step is going to be locate mins and maxes. And then we're going to plug our endpoints and our critical values, our critical numbers, into our original function. To find critical points. because we think that this might be an absolute minimum, right? It looks like it, but let's just make sure. Okay, so our original function was f of x, let me write this down, f of x equals x cubed minus 27x. So we have three values that we're going to be plugging in here. We have 0, 4, and 3. And technically, I'm going to go back here really quick and correct myself. This right here where I put to find our critical points, you're going to be finding, these are just your end points. So we're going to find, we'll say and end points. Because these are our end numbers, right? But if we want to know the corresponding y value, we would have to plug it into the function to find them. So this is going to be endpoints, and then this is going to give us a critical point, which is where our graph is changing direction. All right, so let's do this. So we have f of 0 equals, so if you plug this in, you're going to get 0 cubed minus 27 times 0. You're going to get 0. Now remember, f of x is the same thing as y. So you plug in an input of x, and your machine gives you an output of a y. So now you have a point at 0, 0. Now f of 4, you're going to get 4 cubed minus 27 times 4. And we'll plug this in our calculators. And I get negative 44. This means that that's my y value. So I have a point at 444. So on this closed interval, I have a 0, 0, and I have a 4, that was a lot of 4s, a 4, 44. That's going to be where my endpoint is. And then, let's do my critical value here. So we're going to have 3 cubed minus 27 times 3. And this is going to equal negative 54. Okay, so then I have a point at 3, negative 54. Now let's see, because we saw on our graph that it looked like we were having some increasing and decreasing, which looked like an absolute minimum. Well, if we look right here, we see that we do this negative 54, because when you're looking at minimums and maximums, it's all about what is your y value doing, right? So you're plugging in these critical points of x, and you're getting an output of y. We want to know what y is doing, because that's going to determine how high or how low our graph is going, right? X doesn't determine how high or how low. It just affects our coordinate system of the y. And so you'll see here that when we plug 3 in as an x, we're going to get a really low place, which is what we saw, that it was going to be a minimum. So we have an absolute minimum, not just at x equals 3, but we have a point at 3, negative 54. Now, that's not all that we see here. We see that on this closed interval, we also have an absolute maximum. And that is going to be, oops, let's make sure that's negative, because we have a negative right there. Our absolute maximum is going to be at 0, 0, because 0 is higher than negative 44 and higher than negative 54. So if you have a question that says locate the absolute extrema on a closed interval, these are the things you're going to want to do. You're going to want to take the first derivative and simplify. Then you're going to set the derivative equal to 0. Solve for x, and that's going to give you your critical numbers. But you only, let's put that on here, only use critical numbers that are in your closed interval. Now this is only for closed intervals, okay? If it's an open interval, then you're going to have relative max and mins, and this only using critical numbers that are in the closed interval won't apply. Then you're going to do a number line with the test values, and you're going to see, get a visual of what's going on. And then you're going to plug those test values into the derivative. Okay, and that's going to let you know where you're increasing or decreasing. Then you're going to locate your mins and your max, is what we saw. And then you're going to plug your endpoints of the closed interval and your critical number that applies within that interval into your original function, and you're going to get some points. And those points, based on what their y values are going to confirm what you saw on your graph, that you have an absolute minimum at 3 minus 54, and then an absolute maximum you'll find out from plugging those in at 0, 0. Okay, let's do another one. Okay, so it says locate the absolute extrema of the function g of t equals t squared divided by t squared plus 5 on the closed interval negative 5, 5. So what's the first thing we do? We take the derivative. Now this is going to be a quotient rule. We'll say g prime of t equals, you're going to square the bottom. And if you're not real sure about taking derivatives, I did do a video on taking derivatives, and there's lots of other really helpful things online too. But you really want to be good at taking these derivatives by now. So just practice, practice. Okay, then we're going to write the bottom as it is, times the derivative of the top, minus the top as it is, times the derivative of the bottom. All right, and then we need to go ahead and, well, I'm not going to distribute here. I think I'm going to take out a 2t, factor out a 2t, and then I have t squared plus 5, which I'm putting this back in because I factored that out of both. And then I'm going to have minus t squared all over t squared plus 5 squared. Now, the top is the only thing that can make this equal 0. So, well, it's the only thing that can make it equal 0, but your bottom could also make it equal 0, but not in this case, and let me explain why. So you see here we have in the denominator t squared plus 5, so we don't have any vertical asymptotes, and that's because this will never be 0. Even if t is 0, it's always going to be plus 5, so it's always going to be plus a little bit. Now if this was minus, you would have some vertical asymptotes here, and that would show up when you start to graph things, and you would also plug them in if they apply to your closed interval to see what's going on there and get some points. Okay, so now that we see this, we see that these are gonna cancel, and we just have 2t times 5 over t squared plus 5 squared, which equals 10t divided by t squared plus 5 squared. Okay, so now what we're going to do is we will just go ahead and plug our endpoints. Oh no, we just need to, sorry about that, I got ahead of myself. We want to see what'll make this equal 0. So we'll say this is step 1. Now let's go ahead and see what'll make that equal 0. Well, that equals 0 when t equals 0. So you have a critical value at 0. Now, is this critical value inside of your closed interval? Yes, 0 does fall between -5 and 5. So let's go ahead and let's say -5, 5, and 0. We'll look for these real quick. I'm going to skip doing the number line on this one since the question doesn't specifically ask it. I know the first one didn't specifically ask either, but I think it's a good visual. But just so the video doesn't get too long, I think I'll do a graphing video that has more of the visuals in it, and we'll just do the math stuff for the rest of this video. Okay, so negative 5, 5, and 0, these are your points, or excuse me, these are your numbers. And so we want to find, using the original function, what point these numbers correspond with, what y value. Oop. Okay, and so this is going to be 25 over 25 plus 5, which is 30. Take 5 out of each, you're going to get 5/6. All right, now if you do this for g of 5, you're going to get the same thing, right? Because you're just squaring it. I'll show it though. You're going to get 25 over 30 equals 5/6. Okay, and then at 0, g of 0, you're going to get 0 squared over 0 squared plus 5. Well, as long as you have 0 divided by a constant, it's valid, and so therefore it's just going to equal 0. So that means you have a point at negative 5, 5/6. You also have a point at 5, 5/6, and at 0, 0. So that means that we have, now remember, this is a good example because you would think, okay, well, is this, a less amount than this one? Well, remember, we're only looking at the y value when we're determining extrema. So we have an absolute, because we're on a closed interval. We have an absolute max at 5/6. And you could, either one of those points, you would have both of those points would give you an absolute max. So I'm guessing that, well, let's see, and then you have an absolute min, and you could graph this. I won't graph it. I was tempted to just start trying to graph it to show what it would look like. I think it'd be interesting, but we'll do that for another video. At 0, okay? Remember, because you're looking at these y values. Okay, here's another one. So it says locate the absolute extrema of the function f of x equals 2x divided by x squared plus 1 on the closed interval -2, 2. Okay, so first thing we're going to do is take the derivative. So f prime of x equals square the bottom as it is, times the derivative of the top, minus the top as it is, times the derivative of the bottom. And then we need to go ahead and put these things together. So let's distribute. We have 2x squared plus 2 minus 4x squared all over squared. Okay, so now let's combine like terms. If you see here we have a 2x squared and a negative 4x squared, you put those together and you get a negative 2x squared plus 2 over x squared plus 1 squared. This can be simplified. Okay, so let's take out a negative 2, and you get x squared minus 1 over x squared plus 1 squared. Okay, then we're going to set this equal to 0. So we set the first derivative equal to 0. Well, what will make this equal 0? Well, it's not going to be your negative 2. It's going to be when the x squared minus 1 equals 0. So we're going to have x squared equals 1, x equals plus and minus the square root of 1, which square root of 1 is 1. So you have x equals plus and minus 1. Now, you then check, is plus and minus 1 on my closed interval? They are. So we're good to go. Both of these will be applying in this situation. Okay, so then what we're going to do is we're going to take the negative 2 and 2 and our two critical points, or excuse me, critical numbers. Numbers are not points until they have a partner. So for 3, we have -2, 2, and then 1, and -1 that we're going to be plugging in to our original function, f of x. So we have f of -2 equals 2 times -2, 2 squared plus 1, which is going to give us -4 over 5. So we have a point at -2, -4/5. And then f of 2 equals 2 times 2, or 2 squared, plus 1 equals 4 over 5. So we have a point at 2 4/5. And then f of 1, it's going to be 2 times 1, 1 squared plus 1. You have 2 over 2, which equals 1. So we have a point at 1, 1. And then f of -1 equals 2 times -1. We have -1 squared plus 1. This is going to give us a -2 over 2, which gives us a -1. So we see that we have another point at -1, -1. Now, that means that we have an absolute max here at the 1, 1, because this y value 1 is higher than all these other y values. And it's the y value, remember, that determines our extrema. And so here we have our lowest y value is -1. So this is our absolute min. And now this occurred, both of these occurred at our critical numbers. So this is happening in between our endpoints, not on our endpoints. Okay. And if we did this on the number line and we took all of these critical numbers and we plugged these critical numbers into our derivative, remember critical numbers go into your derivative. To find points, you take the critical numbers and you plug them into your function. So points, plug into the function, critical numbers, plug into your derivative. Okay, let's do another example. Okay, so this problem here says locate the absolute extrema of the function f of x, which equals x to the 4th minus 2x squared minus 3 on the closed interval -1, 2. First thing we're going to do is take the derivative. So f prime of x equals 4x cubed minus 4x minus nothing. Right, because that's a constant. All right, then we're going to set f prime of x equal to 0. So 4x cubed minus 4x equals 0. Oh, did y'all see what I just did? I didn't simplify. I was about to make my life hard for no reason. So let's go back. Oops. All right, so we can take a 4 and an x out here. And that's going to leave us with an x squared minus 1. See how much easier this is going to be than what I was about to do to us? All right, so take the 4x out. You see how I can factor that out? Then if I have 4x times x squared, I would get 4x3 and then minus 1. Okay. So what is going to make these things equal 0? Well, that means that one of my parts here has to equal 0 to make this 0. So in order for that to happen, well, for this one, x would have to be 0. And for here, x would have to be plus or minus the square root of 1, which would be plus or minus 1. So I have these values right here that are going to be critical values for this function. All right, so then after I've done that and we've set it equal to 0, Now we are going to plug these critical values back into our original function just to make sure that we're finding out where our absolute mins and absolute maxes are. So here we go. We're going to find the points. We have f of -1. We're going to do, well, let me write them down. So we have -1, 2, and then we have our critical values of 0. And then you see here we have plus and -1. Well, that 1 is already, the -1 is already taken care of by one of our endpoints. So we don't need to rewrite that one. So f of -1 equals -1 to the 4th minus 2, -1 to the 2nd minus 3. That's going to give us, well, anything to the 4th power is just going to put it, it's going to make it even. So if you have -1 to the 4th, that's just going to be 1, which please practice on your calculator, because let me see, I'm going to do this right now. I have this calculator, which is awesome, but when I plug in a negative into a square root or to a raise it to a even power, like if I square it, my calculator still makes it negative, even though that's not correct. I wouldn't know that if I didn't practice with my calculator. So practice with your calculator before the test, the one that you're going to use for your test. Okay, so I have -1, oh, that becomes +1, minus, well, -1 squared is a +1, so we have a positive times a negative, that's a -2, minus 3. 1 minus 2 minus 3 is -4. So that means we have a point at -1, -4. All right. And then f of 2 is going to be 2 to the 4th minus 2 times 2 squared minus 3. Let's see. 2 to the 4th is 16, minus 2 squared is 4, so 2 times 4 is 8, that's -8, minus 3, that's 8, minus 3 should be 5, so that'll give us a point at 2, 5, and then we have f of 0. Well, if you plug in zeros here, you're just going to get a -3, so we have 0, 4, minus 2 times 0 squared minus 3. That equals -3. So we have a point at 0, -3. And then we have 1. So f of 1 equals 1 to the 4th minus 2 times 1 squared minus 3, which is going to give us 1 minus 2 minus 3, which is still -4. So at 1, -4, we have a point. Okay, so then we want to look at all of our, what was that? All of our y values to determine where we have extrema at. So we have our lowest here, looks like is going to be at a -4. And our highest is going to be at a 5. So these are our points. I should probably, we have a point here, here, and here. So the lowest of those y values is -4. So we can put, we have an absolute minimum, y, remember that's our y value, at -4. And an absolute max at, just set it, where is it? 2, 5, so at 5. All right, so these are going to be your absolute mins and maxes on this closed interval. And I'm going to stop the video here so it doesn't get too long. And I'm going to do another video where we go over how to find more in depth that increasing and decreasing and showing that on our number line. All right, I hope this was helpful.